Should we start the afternoon session? So if you have noticed, the policy for the food that we had for this course is that we give food which is heavier to digest than the information we give you. So you think the course is easy. There was something else I had to say. That was actually a serious information. So, too bad. Oh, yeah, I looked over for the C++70 guaranteed copy elision. That happens when you assign to a pure R value. So if you have a temporary object, or when you return a pure R value. So you return an object constructed on the return statement. That is guaranteed to be copy elision.
So name the return value?
Yeah.
It's still not guaranteed.
You're still not guaranteed. But for instance, I have a code here that I was going to show you at some point. This is a breadth first search on a graph. Initializes in the blue line an STD vector, which is the output, initializes with some values, then push back stuff in there. And then it return out. And out is simply an STD vector. So in the signature of the function, you will have the return type is a vector of that thing. And this does copy elision in GCC. So I checked that the code actually does it. The problem is that this one requires the compiler inspection, right? If you have a return statement and something there, that's very easy. You know that the thing will be constructed where it has to be assigned. Easy. This one is not. The compiler has to go here and see that the return value is this guy, and this guy is instantiated up here. So instead of instantiating out on the stack, wherever it should have been, it will be instantiated on the return where the object will be assigned after the return statement. So the compiler is doing these for you, and it does this copy elision. But it requires the compiler to understand that it can do that. So the guaranteed copy elision it happens in C++17 only for those simple cases. For more complex cases, you still need a smart compiler for doing it. So we were left here. Yeah, and we introduced the default constructor there, is saying, okay, I don't have to write the code here, it's so trivial, the compiler can figure it out for me. And this leads to the fact that you can default and you can delete constructors. Okay. A default constructor is that the compiler provides the implementation as if your class is a POD. Right, is a plain old data type. So it will do, in a copy constructor will do a member by member copy. A default will initialize, default initialize all the data members. Or if there are data member initializers, like this int a42, will initialize the value of a to 42. Another thing you can do is to delete a constructor. The rule here is the following. A deleted constructor cannot be called, but it's there. It exists. So suppose now we have this struct x, which is similar to the y, as a data member a initialized to 42 by default, as a default constructor, which is defaulted, and you have this is called the move assignment operator, which is deleted. Now, we didn't discuss the move semantics yet, right? But this is just a constructor that allows, that if present, would allow an object to be constructed by stealing the guts of some other object. So instead of copying the object, you can steal a few pointers and get the same effect. And this will be more efficient. We will talk way more about this tomorrow, I guess. But now this is deleted. Now when I run this, I create X by using the default constructor. I will call this guy. And now when I do my X, I want to instantiate Y starting from X, calling the copy constructor. Now the copy constructor is different by the move constructor. The copy constructor goes into the class and copies everything from one place to the other. The move constructor is more advanced, and we will see, but they're not the same thing, okay? These will not call this deleted function. We'll call the copy constructor. And the problem is that if you compile this, you get a compilation error. And the compilation error is, oh, I cannot call the copy constructor. This is the signature of the copy constructor. It's implicitly declared as deleted because X declared a move constructor or move assignment operator for X. So the move assignment we have declared here is deleted, so it's not there, right? We cannot call it, but it's actually there. It's there, it cannot be called. This means that there is a move assignment, and the rules of the standard say if there is a move constructor, do not create the copy constructor. So this code will create an error. An interesting thing is that you can delete any function, even a global scope as a member function of your class or a constructor. You can delete every function, and that will make the function not callable. And will give a compiler error when you try to do so. The rules for automatic generation of special member functions, this is the official name of this thing, is that the compiler generates copy constructors, move constructors, default constructors, destructors, etc. for you if there are certain conditions are satisfied. This is the full set of conditions. We're not going through all of them, but for instance, a move. This is the one that concerns us. The move assignment operator is automatically generated if there's no move constructor and move assignment operator. This was also for the move, for the copy constructor. The move constructor is constructed instead if no copy constructor is defined. So there are all these rules that says when something is created for you or not. Now, it might be interesting to know why these rules apply. Why they put all these rules there, why they don't just simply generate the functions for you. Well, for instance, the first one, the default constructor is generated if no other constructor is generated. If I'm specifying a constructor that takes some values, it's probably because I need that constructor to exist, and I want to control how my class is instantiated. If I create also a default constructor, the user can write something that I don't know how to deal with, that I didn't expect. Oh, okay, let's see another one can be interesting. If a destructor is declared, the generation of a copy assignment is deprecated, okay, because before it was doing it. But the idea is that if I need to destroy my classes, it's probably not easy for me to copy these things. If I need a destructor, it's because I allocated something on a heap somewhere, and I need to for instance, do a free or a delete during the destruction of my object. Now, I don't know, the compiler do not know what you did with your class. So if it generates an automatic copy assignment, it might be doing the wrong thing. For instance, you copy the pointer, and then when you destroy the second object, you free, And then you destroy the first object and you free the same area. Then you get a runtime error. So all these things are there for some reason, right? Because the semantics implemented will make it difficult for a compiler to make the right choice. If the compiler can make the right choice, it will do it. Otherwise, it will not. That's the basic idea. If you have more questions, I don't want to go through all of that. It's just a set of rules. So let's go back to the example that we have earlier. Right? We have our struct, and we have the deleted move assignment that basically prevent the copy constructor to be instantiated. Now we have to we can put like a const ref other. We can put a copy constructor as signature, right? X that takes a const ref to some other object and set it as default. And now this code compiles. Because we are telling the compiler it's safe to do it. I'm just picky on the move, but it's safe to do it. And it will do copy data member by data member. Now, we didn't talk about the move constructors and the move semantics yet. We will talk tomorrow about it. The idea is that the move allows you to steal the guts of something. If I have to move a vector, instead of copying all the elements of the vectors into a new vector, I can take the pointer to the memory and the size, copy only that in the new object, and I get a new object with the points in the same storage. Of course, I have to remember to set the other vector pointer to null pointer, for instance. So there are no two vectors that point to the same storage. But in principle, I can move a vector by basically issuing two instructions instead of a for loop. So performance-wise, the move semantics can really help a lot. So we talked about the copy initialization. Copy initialization happens when you instantiate something through assignment, say AX equal something, that is copy initialization. Or when you pass an object by value to a function. I call a function of X. Copy initializes the argument of the function. So in this case, for instance, I have f of y. F requires an input of type t. This will basically copy y into x, because it's by value, it's not by reference. And then the function will do whatever it has to do. So in this case, the mental model that comes is, okay, when I construct x, I construct it using these syntax, x, y, which is the copy constructor. I copy y into x. And then x is copy constructed. This requires x to have a copy constructor. If it doesn't have a copy constructor, you cannot call this function because y cannot be copied in. If I'm doing if I'm creating the object on the fly here, I construct the object t on the fly in that function. That is a special signature. That becomes an R-value reference. We'll talk more about this tomorrow. And this allows x to be moved. So actually t to be moved into x. So this copy initialization is actually moving the object there. And the same thing when I'm forcing it by using std move, then I construct x by moving y into x. So potentially a more efficient way. Now, this will work also in this case. Now, t has a default constructor. as a default copy constructor, and it has this strange constructor that takes, this is called the R-value reference of t, and an integer which is by default 10. This will still work, okay? The mental model is basically I construct x with whatever is in my function call. I construct x with y, or I construct x with t curly braces. That's the mental model. This is what we think is happening. Well, it is actually happening, because the constructor which is called in this case will call this constructor here, in which the second default argument is 10. Okay? To overload resolution, we say I need a constructor that does these, which is the best one. Well, the best one takes an R-value reference and takes an integer equal to 10 that I don't need to pass. Let's see. Yeah, I guess this is it. There are a few little details, but yeah. Any question? Is it clear what the mental model is when you pass an argument to a function? Yep.
I don't get if you do the move constructor, then what happens after exiting the f function then with y?
When you exit this guy, x will be destroyed.
So then, yeah, what happens with y then? I mean, if you move y to x.
Yeah, this is the point. Yeah, the point is that if I can move, it means I will leave y in a consistent state in my move constructor. If I misimplement my move constructor and I leave pointers around, then I get unexpected results. And we'll see that tomorrow when we talk about the move semantics. So when you move an object, you have access to the other object, and you need to keep the other object in a consistent state, otherwise you get in trouble. But it's a good thing, because this one, okay, we don't care, right? This guy will be gone after that sentence, but y will be available after this function. So the move constructor should guarantee that y is still in a consistent state. It has to be empty, it has to be nullified, whatever we want to do with that object. Okay, I have presentations about more specific topics that probably not interesting right now, so we can move to the next argument. Yeah, we can. If we have time, we can do the alignment stuff and the bit fields in one of the next sessions. Everything clear? Okay. Basics again, basic 2.0. Name resolution, type deduction. Let's try to understand how C++ mechanics works. The first thing, okay, let's go with the name resolution. When the compiler goes through your code and see a name of something, like a name of a variable or a name of a function, he has to find what that thing is. He has some internal tables and say, okay, this is a variable of type integers, this is a function, but he has to find the thing. And there are two major mechanisms that C++ uses to find names. One is unqualified name lookup, and the other one is qualified name lookup. Let's say the qualified name lookup is the easiest in some sense. You search for names which are on the right of the scope resolution operator, column. In this case, for instance, A, column, N, when I'm looking for N, then I go on the left and say on the left there might be just a class name or a namespace. So I go to my table of classes and the namespaces and I look over there for that symbol. If I don't find it, I say, okay, sorry, that cannot find A among classes and among namespaces. So the thing which is on the left of this scope resolution operator, this is, by the way, quite important in what we do with templates, right? This scope resolution operator. Whatever is on the left is either a class, a namespace, enumerators, or maybe like a full form template. The unqualified name lookup is when the name appears without the scope resolution operator. Like in this case, this line here, this works. Int A equal 10. When it goes, this declares a variable A of type integer, and when I say A equal 10, then it goes for the unqualified name lookup, and it goes into the current scope, in the outer scope, in the outer scope. So it goes looking for the symbols around. So the current scope is the main function. If we had like a namespace, it will go in the outer namespace and the outer namespace, etc., until it finds the symbol A. This one is a qualified lookup because N is looked only when on namespaces and classes definition. What about this guy here? Does someone knows what happens to this guy? This is actual code. So you can write this code and compile it, and we get a compiler error because what is happening here is unqualified lookup. This is an unqualified lookup of A, which goes and says, oh, what is A? Oh, A is an integer. It's just a variable. And now it's saying, is it an integer and another symbol that I don't know what it is? So you get a compiler error that says, oh, I'm expecting a semicolon before B. Very confusing error message if you don't know what's happening, because A is actually looked over here. Everything clear? This qualified versus unqualified lookup brings one of the strangest thing in C++. If you let's say, I found it very strange when I first encountered it. I said, what the hell is this? This is actually a very good explanation on why it has happened, and we'll try to explain first why, and then explaining how it is implemented. But the question is how this thing works. What happens when I call stdc out, less, and a string? Any idea? It's quite obscure. In fact, what happens, you need to look at the function equivalent. This is a notation to call a function which is operator less. Right? So this actually is it's an infix notation for that operator. It just looks like an operator, but it's actually a function call. And this function call is operator less stdc out hello. The problem is that where is this operator? It's not qualified with a namespace. How do I know? How did the compiler knows that that operator is in namespace std? It is called ADL and is argument-dependent lookup. something that almost never bites you, but when it does, it hurts. And so what happens is that the compiler goes into the arguments and say, okay, this is std cout, this is just a literal some kind, and well, I go look for operator less less in the namespace std because my arguments are std, so I guess the user wants something from that namespace. And so that works because the operator is looked for on that namespace. So what's wrong with this one? Should this work? It has to be, exactly. If we go to the function equivalent, it's operator less std cout and L. Operator will be looked at in the std namespace, but not the argument. The argument is and L, and it doesn't know what and L is. You have to put std column and L to find the symbol.
For the streaming operator, it looks for it only in the namespace std or also in other namespaces if it doesn't find it?
It looks also in other namespaces if it doesn't find it. Yeah. And this leads to the problem I'm going to show you in the next slide. So let's look at this code. We include vector, include algorithm. We do, in our main, we create std vector int, and with some size, and we do for each, v begin, v end, and this is a lambda expression. We will do later, we'll increment all the elements of this vector, and here we have our for each in our global scope, and it takes 2 iterators and called standard for each. So the question for you is this code compiling? Who thinks the code compiles? Who think it doesn't compile? Who close their eyes and hope for the best? Again, this code doesn't compile. The reason is that it will give you an error. I don't have the error message here. The error message is that it is ambiguous. So vBegin is a standard vector argument, so it will look for each into the std namespace. It will find one. Then it goes, well, look, let's see if there are better overloads of this guy. And he finds also this guy here. I say, oh, wow, he has the same signature. What should I do? Should I call the std implementation, or should I call the user implementation? And the problem is, it doesn't know what to do, and it gives you ambiguous symbol, ambiguous function, and it barfs at you and say, oh, well, I cannot choose among these 2 functions. So if you want to call your own implementation, then you have to put explicitly the column operator, transform this into a qualified lookup for the for each, and this goes to the global namespace. I can show the code if you're interested in seeing in action, but it's just going to show you the error. Is it clear why this happens?
But if the signature were different, it would be fine.
Yes. Well, yes. They are different in the sense that one has to be more specialized than the other. In this case, it's not easy to make it. Yeah, this is one of these examples which is not easy to specialize the thing. Which brings the next thing, which is the overload resolution. So now we have 2 functions there, and the compiler says, I don't know which one to pick. Well, actually, usually when you call a function and you call it the member function, there are there are several options where the compiler can look for and decide which one to pick. And of course, the rule must be clear, right? Otherwise, someone writing code would not be able to control what happens. So to determine which function to call, given there are many, many options, is to find the one that is the most specialized, and which means there are the least number of conversion operations to be done. So it's not the namespace, right? We saw namespace doesn't enter into overload resolution, but you go with the arguments and say which argument best matches, which are the functions that requires the compiler less effort to be called. And here we have one test. We have these three functions, one foo requires 2 integers, one that requires a float and an integer, and one is a template function that requires a type t and a type int. And now I'm going to ask you which one is this guy calling? 1, 2, or 3? Who's for 1? Who's for 2? Okay, who's for 3? All right, good. It's 1. It's 2 integers, and we do 2 integers. Which one is calling this one? You have 3 and 4.3. 1? Who says 2? 3? And this is 1. Why? Because integer is already integer, doesn't need to convert anything. 4.3 is a double, which it has to convert in any case. All the 3 candidates requires to convert the double, so it doesn't matter for that argument which one to pick, and the first one is more specialized. Now, 3.4 and 4. Which version is picked? Number 1, number 2, number 3? No one with number 3. Number 3. It's a double. Exactly. This is a double, it's not the float. And for the compiler, converting to a double, to an integer, to a chart, it doesn't matter. It doesn't think, oh, a double and a float are similar, let's do something that the user would expect. No, it's a conversion operation. It doesn't matter what the type is, which means this is a double, it has to convert this one, it has to convert this one, it can just pass the double as a template argument. So number 3 is picked up. Nice, I tricked you, happy. Now this one should be fairly obvious, 3.4 float, and 4 will go to number 2 because it's a float, it doesn't need to convert anything, so it will go to number 2. What about this one? 2 doubles. Number 1, number 2, almost there. Number 3, yeah, number 3, good. Should we go? Yeah, let's go with this one too, right? So 2 floats now. Which one is picked up? Number 1, number 2, number 3. Oh, kind of. No, number 2 is right. Because it doesn't have to convert the float, and it converts this float into an integer, which you will have to do anyway here. Usually the trick is when you are developing these things, you just try out and see what happens. If you know the rule, it might help you getting faster to the solution, but whenever you're coding and you find out the wrong function is called, well, just go there and look what happens. Yep?
Are implicit faster and template specialization treated equally? Like it counts the total number of conversion and translation?
Yeah. Basically, yes. Well, the template argument substitution in this case is really doesn't mean it just takes the type and puts there. So it doesn't have never to do a conversion. If you have a specializations, then the specialization goes and fight with all the other guys. So if I have a specialization for a char, that will get into the fight with the other guys. But this, we don't talk about specialization for function templates. We usually talk specialization for classes. And we'll go into this. Now let's remove the template version. Let's keep playing with this game, right? And now we say we pass 3, 4. Which one is for 1? Which one is for 2? All right, good. This one. Okay, what happens here? Which one is for 1? Which one's for 2? Wrong. Error. He has to convert these argument anyway. Right? 4.3 is a double. It has to convert the second argument. Either to convert to an integer here or to convert to an integer here. And so, and 3 is true. You have to do it also here. But he doesn't know which one to pick up. He has to convert. He doesn't know which one to pick. This is actually not kind of confusing with the answer I gave you earlier. And we might try it on the code. Okay, so let's go like this. We'll make overload version 2. Now this compiles. We put the functions that we were looking at earlier. And dot. So the candidates int and double is ambiguous because I guess the code is wrong on the other in the slide. Yeah, I inverted the thing. We should try it then. Let's be full. Is float an int. Okay, still gives an error. 3.4 and 4 gives an error again because he has to convert the first argument into this one and into this one. It's not the same case, sorry. So I'm really sorry, guys. It's not the other one. Let's take only the one that we care about. This one should compile. Yeah, exactly. Yeah. Okay. So my slides is wrong. Sorry about that. So, oops. So in this case, as we were pointing out earlier, this one requires the conversion of just this guy. So it will call the first one because it doesn't have to convert the first operand. Sorry if that was confusing. My slides has an error in my slides. Any questions anyway? Did I confuse you too much with this thing? A little bit? So let's go back to the code. Okay. So this guy, you have 3 and 4.3. And the first argument are two integers and one float, an integer. So this guy, to call this, has to convert both arguments, the integer to a float and a double to an integer. And this guy has to convert only the double to an integer. So it is more specialized. That's the basic rule. So the minimum effort, the compiler will try to call the function which requires the minimum effort in terms of type conversions. I guess since the code is wrong, I cannot really rely on this anymore. So if we want, I can do this one is a float and double. Yeah, I don't feel confident in showing you the rest. Yeah, this is just the first example with simply the arguments inverted. So the idea is that if I have a 3.4 float, a 4.5 float, and when I call these guys, I will have an error because of this guy will try to kick in and will try to convert. I would rerun these examples. Let's go to one C++ 11 most celebrated keywords, which is the auto and also decal type. And the idea is that why we have auto. And auto perform basically uses the template deduction strategy to get the type of a certain symbol. So why do you want auto? Well, auto basically reduces the number, the code that you have to type in. For instance, if I have a tuple, which is like a sequence of values of heterogeneous types, so a tuple of which contains an integer, a float, a chart, and a string, and I constructed with a 42, 3.14, z, and hello. This will be a sequence of different types, of values of different types. Instead, I can do simply auto, make tuple with these values, and the type of the tuple will be deduced for me. Okay, so the auto is really a quick way of doing. Basically, it can save you a lot of typing. You don't have, sometimes when you are in very complicated libraries, the type can be very long to type down, and so auto will really save your day. But also, other than saving you typing, it also allows you to do something more interesting. Suppose I have a function here that takes a function, it takes this an object of some type in there, right? It's a template function, so I pass some type t there, some object of some type, and I call the member function value out of f, and I say auto x equal fw. Now the type of x will be determined when I call this thing, when I instantiate this function for that particular type. So if I have a function, if my object dot value return a string, x will be a string. If f dot value is an integer, x will be an integer. And I don't have to do anything special here, it will just work. Well, it will not work here when the integer has to be returned. F dot value should return something which is convertible to an integer, but that is another error. You got an error here when you return the value. But this line will always work as long as the f value returns something out of it. In C++, let's say pre-11, so C++ 03, C++ 98, you could have implemented something like this, but you have to be explicit about the type all the time. So you have to have like a contract or an API specification to say whatever type t comes into foo must have, other than the dot value member function, should also have a column value type defined on it, which is a type def inside the function that says that my value type will be integer, for instance, or a string. And you have to type name, t, column, value type x, etc., etc. And this gives whoever implement the object that goes in has to prepare the class to be ready to be used by this function. While using auto keyword, it will work with any class basically that has the dot value member function. Is more less clear? You want to understand what I'm trying to convey here? Another thing, once we have auto, the problem is when, okay, I have auto x, and I guess some type. How do I know what type it is? If I have somehow to get the type back, how can I get the type back? Well, the keyword decal type has been introduced in C++11 just for this, which basically retrieves the type of an expression. The decal type is surprisingly useful in many occasions, and we will see a couple of examples. But first of all, let's see what decal type of 10 is. What do you think this will be transformed into? Int. Exactly, it is just an integer. Decal type of x, where x is an integer, is an int again. Decal type of x plus 10, this is an expression. What's for double? Well, it's still an integer. Still an integer. What is this? This is just a trick. But you should be aware of something like this. This is an expression, a parenthesis expression containing x, and these return, surprisingly, a reference to an integer. That's life. Because if I do x plus 10, and I return something from there, I get an int. Because x plus 10 is an R value, and it is not a reference to a value, it's just a value. Apart from, if I don't consider these tricks, what is the return value? What is the content of this decal type foo? Where foo is a function returning a pointer to an integer that takes a float and a double as arguments. Any idea?
I would guess it's either int star or a function pointer.
Yeah, it's a function pointer. Is this guy int star, which is the return type, that is a function. Actually, it's not even a function pointer. It's really the function type. That a function that returns the integer pointers and that takes a float and a double. So this is a function type. It's not a function pointer type. In the case of a function pointer type, if I have this expression, int star f, float and double, then decal type of f is really a function pointer. Are you familiar with the function pointers, passing function pointers in C? In C, basically this is kind of the same idea, right? So you have a function, then you have a function pointer. A function pointer is declared with this weird syntax in which the name of the variable is inside here. This is the signature of the function, and this is the return type of the function. What is the decal type of this guy? Of this expression? Yes, it's a pointer to integer. What happens here? This is very useful in many occasions, believe me. It sounds a little exoteric, throw me like that. But basically what is happening here, decal type, the expression inside the decal type is not evaluated, is never evaluated. It's called an unevaluated context. The same thing for size off and some other few cases. Right? You put something into size off, you put something into decal type, is never instantiated, is never executed, is just looked at. What happens here is that basically you say to the compiler, I want to call a function foo with the default constructed float, with the default constructed double, and I want to see what comes out of there. And what comes out of there? Well, it goes through overload resolution. So it goes look to all the foo implementations around there, finds the one that the best matches, and gives you the return value of that function, which is int star. Right? Yep.
Type is evaluated statically. For example, if in the body of the function I throw an exception.
Oh yeah, no, whatever. It's never, this expression is never evaluated. This is why you can have functions that throw exceptions. You can even have functions that doesn't have an implementation, right? It might be just semicolon here. You don't need the actual implementation. And there is one example that comes next that shows that you don't need an implementation. It's just looking for the possibility for the possible things that might be called with that signature. At compile time is why I don't have a code here. It's just you can have a code that does a static assert to check that a type is the same as the other type. What about this case, when we have a function pointer, which is null pointer, any idea what happens? Hmm? It is int star again. The function, even though this function pointer is null, so you cannot call the function, you get an error. If you call, this function is not called. It's simply evaluated. You evaluate the signature and say what happens in the signature. This function returns an int star, so this decal type will be int star. And now the real trick. What happens in this case? Compiler error. The compiler error happens because this function requires a reference to a float and a reference to a double. A reference requires an object to be existent somewhere. I can't just refer to an object that exists. I cannot refer to something that doesn't exist, or something that will be destroyed, or something which is intrinsically const. For instance, when I construct my float and I construct my double, those are temporary values which are basically R values. They cannot be modified. They're intrinsically const. And when I pass to this reference, I cannot accept the reference to a float, to an R value float. Everybody understand the difference between R value and null values? We will see more about this tomorrow. An L value is something that can stay on the left side of an assignment. It's a left assignment. So if x equal something, x is an L value. An R value is something that stays on the right on the assignment, and that can be a temporary object that doesn't exist. So these guys in R values, they cannot be on the left side of any assignment, so you cannot have a reference to it. And this gives you a compiler error. And the compilation error is I cannot call foo with these arguments. So instead, C++11 guys introduced decl val. Decl val preceded by std. Okay, this is std standard library function. So decl type is a keyword of the language. It doesn't need any namespace, but decl val is. So for space reason, I didn't put the std qualification here. But if you say decl type, if I have a foo, now it takes an integer and the reference to an integer. Now it's slightly different signature. I can say I want to call foo with the value decl val of int and a decl val of int reference, and it goes in there. You know why? Some idea how the mechanism works. This requires a little bit of tricks that we'll see tomorrow. It's called perfect forwarding. But the idea is that this is just a function call, just a template function. Do I have the... Okay. This is actually the implementation of decl val. And decl val is the declaration of this function, which is decl val without argument. It has a template and add R value reference to it. So we talk tomorrow about why it's R value reference, but there's no definition. If you try to call that decl val in your program, you get a compilation error that function is not available to you. It's only the declaration. Because decl type is unevaluated context, so you don't need to call the function. You just need to know that it's there. The signature is available to you. Does it make sense? Do you want to see an example where this thing is used?
Is it useful for anything?
Yes. A lot. I'm not quite ready to show you the example. Requires some templates. If you bear with me, I can show you already. Because it might be a little bit abstract. So why the hell do I need that thing? And I have a very nice example to show you. I see some troubled faces. What's the problem?
Like from the example where you used it, this decl val before, like it seems like it needs to be somehow constructible and return something which it considers an integer.
A reference.
Like in the
Yeah, exactly. So
it needs to fake so that I was just...
yeah, it doesn't do anything. Really, the only implementation you can find in STL is this guy. It doesn't do anything. So in theory, you have a function that returns a reference to something, which everybody tells you from C++ 101, never do it. Never return a reference to something created within a function, because that thing is maybe on the stack and can die very soon. You have dangling references and all these kind of problems. So you should never return a reference from a function that doesn't take that reference in. Okay? If I have a function that takes a reference and then return the reference, well, it's just passing through the same object and the reference to that object, and it's fine. But if I create an object on the fly in my function and return a reference to it, that is at least a compiler warning telling you, oh, you're returning a reference to something here, and this is bad. Instead, this guy never tells you anything. It doesn't give you a warning because it is unevaluated. It never looks at what the function is doing. It just looks at the signature and gives you back something. Actually, it doesn't give you the warning because of this R value reference. But that's kind of trick. And it simply works.
Ignoring the warning, you could also just have returned the T reference?
No, you cannot construct... I guess you can.
Just,
I guess you could. Yeah, you can. The problem is that then it will be usable only for purely reference arguments, while this guy works for our value reference too. I guess it will work. So let me, oops. Is it here? Where is it? Oh, shit. No, too soon. Sorry, you flip off with it. too soon. But basically, the idea of the decal type of that you pass a function or one expression is a way to check that expression exists, that is valid. So you can at compile time check that something is valid, and if it's not valid, you can do something else, for instance. You can recover in some other way. I will show you, but we need the templates first. Otherwise, it becomes just even more confusing than what it is right now. C++ 14 introduces decal type auto. Okay, decal type auto is one of these features that you never need until you need it. Decal type auto is a keyword composed of these tokens, right? Decal type auto. That's really a single thing, basically. You cannot put anything else. And then you have an initializer list of some kind or a function call of some kind. The mechanism is quite complicated, but the idea is that when you do decal type auto of some variable, you inherit the qualification of the type you come from. So if I have an integer, an int x equal 10, and I say decal type auto of x equal y equal x, y will be of type integer, right? Because x is a type integer. If I do decal type auto of w equals z, and z is an integer reference, then w is a reference to integer. So it keeps the references. If I put auto here, they will be both int. Okay? Maybe I should. Let's go to build. Let's write some example here, right? So it's let's see how it goes. So now we do like this. We create the int main. All right. Okay. Now we have an int x equal 10 and auto x1 equal x. Now we have int y int ref y equal x. Of course, a reference to an integer requires on the right side an integer which is not an R value. You can only reference to L values. And then we do auto w equal y. And now we do some static assert. Yeah, we do static assert. Now we introduce type traits. Is it with or without underscore? I don't remember. With, right? Yeah. I never remember that. Okay. Type traits, now we say static assert std is same decal type of x and decal type of x1 equal value. Okay. Is someone reviewing my code? Now we get the type of y. Would you expect this to work? It shouldn't work because y is a reference. Y is an int reference, but is w a reference? If I put auto in w, it is assumed that it is copied into. It's a new variable that I copy into. So w is supposed to be a reference. It's supposed to be just an integer. So if I compile this guy, I expect to get the first static assert to pass and the second one not to. Let's do 14 because now we need to do the decal type auto and static assert. See? Static assert. And now this is an example of the static assert. Static assert goes into, during compilation, checks for some constraint. And the constraint is that the type of this type has to be the same as this type. This is a meta function. Technically, we'll go into template meta functions more tomorrow. std is same, is from the type traits. It gives you to take two types and check the types are the same. If they're not the same, the column value, which is a kind of static value, will be false, and then you get an error. I'm wondering if this works. Wait a second. I'm wondering if this works. I never tried. Yes. Now it compiles. Now I'm saying decal type of w, if I add a reference, it will be an int reference, right? Because w is an integer ref, which is equal to decal type y, which is int ref. Now let's try with decal type auto. What would you expect to happen here? This guy should inherit the type of x. So this should be still valid. The two x and x1 should have the same type. It should be integers. But this guy now, w is a reference. So it should be possible to go here, remove the reference, and now y and w have exactly the same type. I hope it works. Yep, compiles. Right? Decal type auto maintains these references-ness of this thing. And as before, they say, why do you need these? Why in heaven you want to do something like this? Well, in generic code, in templated code, sometimes you are defining an API. This API requires get something in input, and you want to say, listen, I don't care what you're passing me, I'm fine with everything. From the same example as before I was showing you with the breadth first search algorithm, you have something like a function that takes, let's say that we have a function in which we pass an array, a sequence of values, and an index, and some function that returns true or false, depending on what the depending on some values. So the function will say, okay, I want to return a reference to a value of this array. So I go into my sequence at my index, and I get the reference to the value type, array column value type. So assume that my array type has a value type defined in that. So the class has that thing. And I do, okay, if the ref dot value if the predicate on this value is true, then I mark, otherwise I don't mark. So this array contains some object which has the value and the mark functions, and you mark if the predicate is true, otherwise you don't mark. Which is a problem because, first of all, you have to type this guy, so the array must have the value type defined in the class. It doesn't mean that you have to write the code for it. And this is what if a smart guy comes in and instead of passing an array, just a regular array, passes something that the operator square bracket returns something else, returns a proxy to an actual object. We will see the proxy. Proxy is an object that behaves like something else but is not the thing. Right? It's like a little class that refers to something but is actually an object. Now, if this return a proxy, it cannot be a reference to that thing because it is created inside the function, pass it by, and you have a reference to a temporary. You get a compiler error here, or a compiler warning here, saying you are referencing something which is temporary. Or what if the array doesn't have the value type defined in it? Then you have another compiler error. So instead, you do like this, decal type auto. So whatever this operator returns, if it is a reference, it will have a reference to a value. Like you pass an array, and you get a reference to an element of that array. Otherwise, it returns a proxy, which is still valid. It would not be a reference. And then you can call exactly the same code. Is it more or less clear? So this is useful only when you write a function, typically template functions that assume that something comes in, and it makes assumptions on that. So you can relax those assumptions by using this keyword auto and decal type auto to relax the constraints, and you can write easier code. This will make the code much better for the user also. It doesn't have to implement many things. Any questions so far? Was it too complicated? Any comments, please? You didn't see the old decal type auto. I hope that by the end of these 2 days, you will have a better idea why these things are needed. These are, as I was saying before, these are just the basics, right? Just the fundamental pieces, and to build over other things, and we'll see later and tomorrow what that really helps, why that really helps you.